Most predictive maintenance systems rely on vibration sensors as their primary source of truth. While a vibration alert can pinpoint when an asset is likely to fail, the sensor data alone fails to explain the physical cause. Identifying that cause involves correlating the vibration with other physical signatures, such as heat or noise, to find the root of the problem. This structural map illustrates a system designed for that correlation, routing distinct sensor inputs into a central AI node for analysis. The architecture ingests three specific data streams: acoustic signatures, thermal infrared imagery, and the historical context stored in maintenance logs. When processed by isolated single-modality models, the system cannot identify the relationships between a frequency spike and a temperature rise. We are examining how a multimodal vision language model is engineered to bridge that gap, correlating disparate unstructured data into a single diagnostic output. Solving the root cause problem requires re-architecting how we process and fuse sensory data at the model level. Disparate modalities must be processed and standardized individually before they can be mathematically fused. We begin with the raw acoustic data captured from the factory floor. To make this audio useful for a visual-based model, we transform the signal from the time domain to the frequency domain, creating a two-dimensional MEL spectrogram. Thermal infrared data requires a different pre-processing pipeline. As this diagram shows, the raw IR image is segmented and converted into a standardized matrix of numerical temperature values. The final input involves the historical context found in human-written shift reports. We vectorize these text logs to ensure the language data is compatible with our numerical sensor grids. A report noting a minor seal leak is transformed into a multidimensional vector using NLP embeddings like BERT. With these three standardized datasets prepared, the system is ready to ingest them into the fusion layer. The core of this system is the multimodal fusion layer. This graph represents a shared embedding space where audio, visual, and textual data are mapped to the same mathematical coordinates. This differs from legacy late fusion models, which process modalities separately and often fail to find the underlying physical connections. We use a cross-attention mechanism to find those connections, visualized here by the dynamic weights forming between the different data clusters. Cross-attention forces the model to mathematically weigh a visual heat anomaly against a specific acoustic vibration pattern. The resulting probability calculation is then constrained by the specific context provided by the historical text logs. The model calculates physical relationships by evaluating weights across all three sensory dimensions simultaneously. This cross-attention block allows the model to identify the causal link between a frequency squeal, a thermal hotspot, and a documented leak. To demonstrate this in practice, let's take a look at a real-world example and consider the breakdown of a large industrial pump. The thermal camera detects a localized 20-degree rise in temperature at the bearing housing. Simultaneously, the acoustic sensor captures a high-frequency spike corresponding to ball pass vibration. Finally, the system retrieves a maintenance ticket from the previous week, noting a minor seal leak. This diagram shows the fusion layer processing these three vectors: the heat, the sound, and the text context. A traditional dashboard would simply report a generic vibration alarm, leaving the specific cause unknown to the operator. By correlating the three inputs, the model generates a deterministic output: bearing failure due to lubrication loss with 94% confidence. This specific diagnosis allows the maintenance team to address the root cause immediately, preventing the failure from escalating into a catastrophic shutdown. Deploying these multimodal vision language models requires addressing several engineering constraints. Large-scale models like Gemini Pro require massive server-side compute for training and high-level reasoning. This creates a gap between the cloud servers used for training and the factory floor, where assets require low-latency, real-time inference. Closing this gap requires a hybrid approach to deployment. We train the heavy multimodal architectures in the cloud using large-scale compute resources. For deployment, the model passes through an ONNX quantization filter, which optimizes the network for small form factor hardware. This optimization allows complex cross-attention calculations to run natively on ruggedized edge gateways located next to the physical assets. Effective predictive maintenance requires moving past fragmented, single-stream dashboards. By architecting systems that fuse modalities mathematically and deploying them to the edge, we can achieve a higher level of diagnostic accuracy in industrial environments.